if I say, let's do this. If I say, right now, if I say, what's the dimension of A? Remember, A is still a vector. It says null, because vectors don't have dimensions. But if I force it to have a dimension, more than one dimension, 2, 3 in this case, now when I say, let's look at A has been transformed into a matrix because I forced it to have two rows, 3 columns. And you have to have a divisible number. Let me confirm that. If this is 5, let's try this. We do this. So A now is just 1 through 5, and then we force the dimensions 2, 3 on it. See, doesn't work. Generally, you can perform math. For example, you can add vectors of different lengths where it will simply start repeating the shorter one. That's the default. But you can't, this is one exception, you can't force a matrix if it doesn't fit the dimensions. Okay, so it has to be, you might make a note of that, it has to be divisible, it has to fit the rows and columns have to be a product, have to be divisible. So if we do that, and then we say print A. Now, same thing with the matrix. You reference, as we'll see shortly, we won't do it now because we're just looking at the 4 structures quickly. But you can reference any elements using the combination. Note now the subscripts have 2 elements. The first one is the row number, and then you have a column. The second one is the column number. So 1 comma blank means the first row, all columns. Or blank comma 2 means all rows, but just the second column. And you can use sets, subsets, to reference a single element in a matrix or any combination of them. Okay, let's skip data frame for a second. We're going to spend a lot of time on data frame in a moment, but lists really are your most versatile and your most useful structures. Lists can do a number of things, or I should say you can do a number of things with lists that you cannot do with any of the other structures. A list is an ordered collection of objects. That's a description I took out of some book. But really, the way to think of a list, just think of all of these other structures. Think of vectors, matrices, data frames, and then a list is just a collection of these other structures where each structure is a component of a list. Each structure is a component of a list. So you can tie together all of the any number of other non-homogeneous structures and put them all into one list where each different structure is a separate component in the list. And you can even include, lists can be recursive, unlike these other ones. Data frames can be recursive too in some cases, but it's rare. A list can be recursive. You can include a list as a component to a list. So you can imagine the possibilities of the odd types of data conglomerates that you can fashion into a list. That's one of its strengths. If you're collecting a multi-year study of different variables and participants come and go and treatments come and go, and you have all of these dimensions and different types of structures to your data, you can't store that in a spreadsheet. A list would be a much better suited structure to store that. Okay, so here, note we're using the list function. there's an analog to this with all of the other structures. There's a vector function, there's a matrix function, there's a data frame function. And it creates whatever's the arguments gets fit into a list. So here is the simplest, where we are naming a component and we're giving the value of a component. And we're naming a component and we're giving the value of the component. And we're saying put that in E. So there's our variable E, and we look at E, and notice how E expresses, how lists express. It looks funny. You get the component with a $sign, and then the name of the structure that is that component. In this case, it's a vector with one element. And the second component for list E is named size, and it's also a vector. The element in that component is a vector with one element, and it's character, 8.25. And you can see what we're trying to do here. It's a list that we would use to store different articles of clothing, where we could name the article in the first component and then record its size in the second. Now you could use other structures for this, but it reflects the fact that you can have different disparate types, different types of information. So here, note we've named the components, but these components, this first one still has an index, which is 1, and this component has an index, which is 2. But lists use double subscripts. Let me show you what I mean. So let's start poking around E. What happens if we just use a plain old 1 subscript with E? It lists out the entire first component, both the name of the component and the structure inside the component. If we do this, though, and I always get these two confused, if we do the double bracket, all we get, no, we get the same thing. I'm sorry. No, we don't. I told you I get confused. The double bracket only lists the element in the component. And you can see my confusion. I'm always stuck on the notion that the double bracket should be the component as a whole, but it's not. It drills down. Think of the double bracket as drilling down inside the component, because that's what it does. Okay, 2, so if we say 2, what is the second component? It gives us the entire second component, name and element. If we say double bracket subscript 2, it just gives us the element inside, so it's drilling down. Maybe I can remember that. How about 3? If we say what's the third component? Well, there wasn't one, right? So it tells us there's no name, there's nothing. It would return a number or name if there was one, but there isn't. List. Why is list useful? Almost all of your functions, all of your complex functions, all of your complex mathematical functions, as well as all of your complex graphic creating functions, all return lists as the object, because that's the only thing that can hold the information that they determine, that they compute. So lists are output by almost all of these fancy functions that you'll be using in your data analysis. But many functions in R that manipulate data, will not operate properly on a list. If you try to compute the mean of a list, if you say mean and you put a list inside as an argument, it doesn't know what you're talking about. Or if you try and say what's the length of an object, will tell you the number of elements. If you say what's the length of some list, meaning to count the number of elements in one of the vectors or in all of the vectors, all it'll do is tell you how many components you have, because lists have these odd shapes. So a lot of functions don't work. So that's a problem with lists. You have to be aware of that. And more generally, That's why you need to know about all of these structures, because invariably you're going to be doing something to them or with them using functions, and functions differ in the structures that they can process. Okay, so we'll come back to that. So here let's create a bunch of vectors. So here's a vector. X1 is just numeric, and you see it populating over here. X2 is character, where actually X2, what is X2? Let's take a look at X2. X2 it's just one long vector. Note what happened. This is a good example. With X2, I had two vectors as the argument. One of the vectors was were strings, were characters. The other vector was not. The other vector, they were integers. And I combined them together, and remember we said a vector they must all be the same type. R had to change one to the other in order to succeed on executing that line, and the only one it could change was the numbers to characters, so it changed them. Here we create just a so-called scalar vector 3, and then we create a matrix as 4. So we have different objects. Here's 4. It looks like this. There's no values in it. We just created the structure of it. Now we're going to enter values. We're going to enter 1, 2 in the first column of 4. So if we look at X4 now, it's got 1, 2 in the first column, and then we're going to enter in 3, 4 in the second column. And so now we've populated all of it. And now we're just going to bind all of these 4 different structures up into a list. And we're going to name them X1, X2, X3, and X4, but then the elements will also be the corresponding variables. So what does uppercase Y look like? Well, it looks like this. So here's our list. It's got 4 components. First one's a numeric vector. Second one is a character vector. Third one, numeric. It could be true, false, could be anything. Fourth one is a matrix. It's two-dimensional. So you can see if you said mean, what's the mean of, let's try it. What's the mean of Y? It's not going to like it. Can't do it. If we said what's the length of Y, which length is usually used to count the elements, it just returns the number of components, 1, 2, 3, 4. So there is a way that we could count individual elements, but we'll do that. We'll save that for later. So you need to know what the structure is when you're running these common everyday functions. Okay, let's look at data frames now. And data frames you're going to use them the most. And so we're going to spend some time on manipulating data frames. Why do we do that? Well, selecting rows and columns, or subsetting data sets, or merging data sets, or creating subsets that eliminate or suppress just some of them, some of the elements, or dealing with missing data in your data sets. These are all very common issues that most users deal with. And these issues are at the data frame level. They're specific to your data sets, your data frames.